Hello there. In this lesson, we're going to learn about how to calculate image distances and object distances, along with object and image heights. And we're going to do that using two equations. First one is called the thin lens equation, and all of the lenses that we have done are thin lenses, so it's going to apply to everything that we've done so far. And then there's another relationship called the magnification equation, where you can determine how much bigger an image might be than the original object. So of course we're going to use all our old favorite incident rays and refracted rays through the focal point. Of course, if you aim through the other focal point, it's going to come up parallel. And of course, right through the middle continues on its way. And that'll give us a spot for our image. All right, let's go. So we're going to need several different measurements in order to relate them with the equations that we're going to be using. And so the first one here is the distance to the object. And of course, you're just measuring from the middle of the lens to the middle of the object, and that's going to be your distance for that part. Secondly, we've got distance to the image, same thing, but on the other side. This is always going to be positive. This is going to be positive if it's on the opposite side from the object, and then negative, of course, if it's a virtual image. The next one, of course, is the height and height of the image. And finally, the focal length, or where the focal point is, will be helpful as well. So the first relationship or equation is called the thin lens equation. And you can see that it relates the distance to the object, the distance to the image, and the focal length. And so distance to the object, of course, it's from here to here. And this is always going to be a positive value. Distance to the image from here to here, that's going to be positive if it's on the opposite side from the object, and negative, of course, if it's on the other side. And then the last thing, of course, is the focal length, and that's the distance to the focal point, which will also be positive for converging lenses like this one. But if it's a diverging lens, well, then it'll be on the other side, and it'll be a negative value for the focal point if it was one of those diverging lenses. Alrighty, so let's use the thin lens equation here to work out a focal length. So this is the value that we want. We have these two, so we should be able to solve it. So 1 over d0, or distance to the object, is the 42 centimeters, so 42 centimeters. And we're going to add that to 1 over distance to the image, which is 30 centimeters. And that's going to equal 1 over the focal length. So if I put that into my calculator, 1 over 42 is 0.0238, and 1 over 30 is 0.0333 repeating. And if we add those up, we end up with 0.05713 equals 1 over the focal length. So to get the focal length, we're going to need to take the reciprocal of that. So 1 over 0.05713, and that comes out to 17.5 centimeters. So the distance from this center of the lens to the focal point would be 17.5 centimeters. So there you go. Alrighty, for this situation, we're given the distance to the object, and we're given the focal length, and we're looking for the distance to the image. So what I would do first is rearrange this so that this expression is by itself. So 1 over di equals the 1 over the f. And then we'll move this expression over to the other side. It's positive here, so it'll be negative on the other side. So it's going to be minus 1 over d0. So let's put in some numbers. 1 over 11 centimeters for the focal length, minus 1 over 25 centimeters. The 1 over 11 equals 0.0909. The 1 over 25 is 0.04. And then if we subtract, we're going to end up with 0.0509. And that equals 1 over the distance to the image. So now we just need to take the reciprocal. Distance to the image is 1 over 0.0509. And if you calculate that, it comes out to 19.6 centimeters. So that would be the distance to the image. So from here all the way over to here, 19.6 centimeters. Now, since that's a positive value, that means that this is a real image. It's on the opposite side from where the object is. Okay. Alrighty, so for this one, we've got a couple of differences. One is that we're looking for the distance to the object, so that's this value. And the second is that this is a diverging mirror, right? So since it's a diverging mirror, the light rays don't actually cross, but your brain thinks they do. And so it's going to be a virtual image, which means both these values are going to be negatives, right? We're going to have a negative distance to the image, and we get a negative distance to the focal point. So let's have a look and see if we can work this one out. So to get this guy all by itself, we'll say 1 over d0 equals 1 over the f, and we'll move that other expression over to the other side. So this should help us solve it. So the focal length is the negative 14 centimeters. So negative 14 centimeters here. And the distance to the image is 1 over, that's negative 10 centimeters. Great, so we can work those out in the calculator. So 1 over 14 is negative 0.0714. And subtracting 1 over 10 is negative 0.1. So that comes out to 0.0286. And so that's 1 over d0. So DO, I should say, is going to be 1 over 0.0286, which goes to 35 centimeters. Great. So that means this distance here, from here all the way to the center, is 35 centimeters. Alrighty, let's see what else we got here. All right, so our next relationship that we're going to look at is the one that gives us the magnification. Use a big M to represent that. And so magnification is the relationship between the height of the image versus the height of the object, or you can do the distance to the image over the distance to the object. And with that one, it's a negative value. So you're going to end up with a value that is positive if you have an upright image, and negative if it's inverted. So this would be a positive M for this guy and a negative M for this guy. All right, let's see how quick we can use it. Okay, so in our first situation here, we have a converging lens, and we're trying to find the height of the object. So this guy here. Let's find the magnification first. We'll do this in 2 steps for this one, and then we can do it in 1 step maybe the next time. So the magnification, we have the distance to the image and the distance to the object, so we can solve it using that. So it's negative di over do. So we'll say negative distance to the image is 24 centimeters. Distance to the object was 32 centimeters. And type that into your calculator, and it comes out to negative 0.75. Great. Now we can use that, we have the M now, we can solve for this guy because we have the height of the image, which is here. So M equals HI over HO, and if we want HO, we can just switch it with the M, right? So HO equals HI divided by M. HI is negative 8 centimeters, and the magnification is negative 0.75. And so that comes out to pretty close to 11 centimeters. Yeah, so there you go. Okay, again, we've got ourselves a diverging mirror. So some of these values are going to be negatives again. And this time, I think instead of solving for the magnification, we'll just use this part of the relationship and just solve for the value that we're missing here. So we've got the height of the objects, we got this guy. We've got the distance to the objects, we got that guy. And we got the height of the image, so that guy. So this is the only one that we don't know, and that's what we're trying to find out here, distance to the image. Great, so we want to rearrange this so that distance to the image is all by itself. And so we can leave HI and HO where they are, and we'll just move distance to the object to the other side. along with that negative sign. You can put it wherever you want because it's multiplication. Right, so then let's put in the values. So it's going to be negative, and the height of the image was 4 centimeters times the distance to the object, which was 64 centimeters, all over the height of the object, which was 12 centimeters. And if you put that into your calculator, you'll end up with a negative 21-ish centimeters. So that means that, yeah, from here to here is 21 centimeters, and it's negative because this is a diverging lens, and you are on the same side as the object. All right. Alrighty, so to finish off here, let's do a problem that involves both of the equations. So I always like the GRASS method for these things to start off with, and that's where you start with what you're given, right? So we're given the focal length, so it's F, and that equals 10 centimeters. Great. And we've got 15 centimeters between the lens and the object, so DO is 15 centimeters as well. And we are looking for the magnification, so we want this guy. So far we've got the distance to the object, and if we want the magnification, looks like we're going to need that one. Let's see if we can get it from the thin lens equation here. We've got the focal length, and we've got the distance to the object, so we can figure that one out there. So let's use this first. So we want 1 over di equals 1 over f minus 1 over do. So 1 over f is 1 over 10 centimeters minus 1 over 15 centimeters. So that's 0.1 and 0.067, and that comes out to 0.033 repeating. So that's 1 over di, and then to get just the di, we can take the reciprocal, so that's 1 over 0.033, which comes out to 30 centimeters. Great, so let's work out the magnification then. So the magnification is going to be negative di all over do, which means negative distance to the image was 30 centimeters divided by distance to the object, which is 15 centimeters. Ooh, look at this. It's going to work out nice and even. So that comes out to negative 2. So you're going to get magnification of 2 times over the original, and of course invert it. All right, hope that helped, and we'll talk to you soon.